Okay, welcome back. So we think of this as a two-step process, and the two important things that happen in sampling can be broken down into these two sort of mathematical operations. Now again, I derived the sampling relationship, the relationship between the spectrum in discrete time and that in continuous time, without using impulses and impulse trains and so forth. And there's a completely analogous way to do the derivation using impulse trains. And I'm going to use that right now, but I wanted you to see that you could do it both ways. So let's go through that process now. If I take the signal XA of t and I multiply it by this impulse train, multiplying two signals in the time domain is the same thing as what in the frequency domain? Well, if I have two signals, x of t and s of t, and I multiply them together in the time domain, then the Fourier transform of the product gives me 1 over 2 pi times x of omega, sorry, make that x of theta, s of omega minus theta, d theta. So I get 1 over 2 pi times convolution in the frequency domain. Now you'll probably remember this as convolution in the frequency domain. If I wrote all the variables in hertz, then d theta over 2 pi, this is the same thing as the integral from minus infinity to infinity of x of phi s of f minus phi df, because d theta over 2 pi equals df, because 2 pi f is theta, right? So in hertz, it's just convolution. In radians, it's 1 over 2 pi times convolution. So I have 1 over 2 pi times the convolution of the Fourier transform of this impulse train with the Fourier transform of x. So let's go back and look again at that relationship. If I have a periodic impulse train, I'm not going to prove it to you, I just need you to accept on faith that if I have a periodic impulse train with impulses that are area 1 every capital T seconds, then that has a Fourier transform. It doesn't really have a Fourier transform, but we say that it does in a distributional sense. We use the Fourier transform for this periodic impulse train in hertz, in f, to be impulses, to also give me an impulse train. At integer multiples of 1 over t. So this is periodic with period t, so it should have energy at harmonically related frequencies corresponding to the fundamental, which is 1 over t. And the areas of these impulses are 1 over t. Now if I were to write this in radians instead of hertz, instead of f, I'll use the variable omega. Instead of these being at integer multiples of 1 over t, they'll be at integer multiples of 2 pi over t. And instead of the impulses having area 1 over t, they'll have area 2 pi over t. Okay, so now if I take the signal xa of t and I multiply it by s of t in the time domain, then I must have convolution of the spectrum. If this is xa of omega, if this is xa of omega in the frequency domain, I must have convolution between xa of omega and this impulse train. I've got a 1 over 2 pi because I'm doing this in radians. So what happens when you convolve a function with an impulse train. You just get a copy of that function on top of each one of those impulses, and this area, the area of each one of the impulses, just scales the area of, or scales the amplitude of xa of omega. Now there's a 1 over 2 pi times the convolution, so these 2 pi's will go away, and I'll end up with a 1 over t times copies of xa of omega every 2 pi over capital T, which is exactly what we expected to get. When I convolve those, I'll get 1 over t, and I'll get another copy at 2 pi over t, another copy at minus 2 pi over t, and so forth. Now this was band limited to b. This is still